I made a shocking discovery today when I was hanging out over at MEUK's Discord server.
Are we gonna keep on fighting? Are we gonna keep on dividing? Are we gonna keep on fighting? Are we gonna keep on dividing? Well, are we gonna keep on fighting? Are we gonna keep on dividing? Are we gonna keep on fighting? Are we gonna keep on dividing? Well, did you hear what I said?
21 minutes past 10. Yeah.
Fascinating. You know, maybe I'll say again.
What you up to?
I think it was just boring over there, and it's sort of. I guess it's quiet here too.
Yeah, Dave was saying it's been rough over there.
No, rough.
Well, yeah, he was just saying it. I don't know. I don't know whether he said boring or whatever, but he's gone over to Ranties and said, I don't know what his words
Dave,
were.
like Rakia?
Yeah.
Yeah, Rakia.
He was getting tarnished over there.
Yeah.
Oh, is that why he didn't say he was running away from? You think that what was happening?
He was getting picked on a little bit earlier. But it's no Biggie Smalls.
Yeah, they do pile on though, don't they? Bless them.
I actually apologized to him not 45 minutes ago.
Yeah, oh, he won't hold it against you. The thing is, in a room like that, it's very hard to keep it civil.
Yeah. Yeah, we have our infighting. But yeah, I posted this thing is for a test. Well, for not really a test, but an observation and measurements I'm doing. That you can include yourself in or not. But I just thought I'd pass it around.
Oh, cool.
What's this for then?
Just for something I'm together. I'm trying to pair people up for an observation regarding longitude lines and subsolar point.
Longitude lines. How'd you do that?
It's in the debate discussion, bro.
Okay.
Right, yeah.
Go on, give us a rundown, because I'm just doing something in me thing.
It's part of a robust video that I'm producing, so it's not really just one form, but this specific bit of data is just to grab people who are along the same latitude line, more or less. So take, for instance, somebody in England and someone in, let's say, the Netherlands. Say they're about the same latitude line. And
yeah, but how do you establish the latitude line? Is that's
right? That's in here too. That's a little bit more trivial, much easier to do, but that's also going to be confirmed with this. But ultimately, to confirm the longitude lines, they're going to be confirming their local solar noon, and that it's occurring where the sun is directly south of them, and yeah, so measuring the time difference between the two places, like the time in which it takes to get from one place to the next, and that sort of thing.
So how do you establish your latitude lines then? Again.
Well, as I said, that is the more trivial part, and if somebody, so in this thing that I posted, they can also do the part where they measure the stick in the shadow, and today I know the sun is directly above about 8 degrees latitude, and so if you live at 58 degrees north, then I would predict that your sun, no, actually no, let's say you're at 52 degrees north, I would predict that your sun should be 30 degrees in the sky.
What do you mean by 50 odd degrees north? What does that mean? Where'd you get that from?
50, that's your latitude, like 58 degrees north latitude.
Yeah, how do you get that?
Like I said, by measuring the sun's elevation at your local solar noon. You measure at your local solar noon, it should be roughly, no, it should be 40 degrees, sorry. It should be 40 degrees if it was 52. So it should be 40 degrees in the sky.
Sextants.
Which would be a prediction I would make.
You're making a sextant measurement.
Yeah, you can use a sextant or you can use the length of a shadow, but you get the same answer either way.
From using the length of a shadow.
That's right.
How do you determine that?
Well, if you had a stick length, like let's say it was a meter stick, and it had a shadow produced, then you would be able to infer that the direction of the sun to be able to create that length shadow, to be able to create that triangle, would have to be in the direction. It'd be going a straight line from that direction. So you just take that.
Yeah, but you just get a different length of a shadow, right? You just get a different length of a shadow, right? In proportion to the length of your stick. How do you know what you're doing with that? I mean, that's just the shadow length, surely.
But just like I said, if you can infer that if the shadow length was exactly the same size as the stick length, so you had one side and the other side, they were the same length, you could easily see how that would tell you that the elevation of the sun was 45 degrees in the sky. And so the same rule applies to about any length. You just take
the elevation of the sun in the sky, because your stick is the same, shadow is the same length as the stick.
That's right. So if you have two sides of a triangle of the same length and it's a right triangle, then the two angles on the opposite side are going to be 45-degree angles.
Right.
So that gives you the elevation angle of the sun from that position.
A triangle though, with 180 degrees. Yep. Yeah, 90, a 45 and a 45. So because you make a triangle with a shadow and a stick, then that tells you
the elevation angle of the sun, or the height in degrees of the sun.
The height in degrees. Now that's we had this with the other day. What sort of height would you put the sun at, because of you've drawn a triangle with a stick and a shadow?
Well, you'd obtain the elevation angle.
The elevation angle. And that would be?
It's going to be different for different people at different times, different positions. But I gave you one example. If you were at 45 degrees
it would be
north,
45, wouldn't it?
Yeah, if you were to get a 45-degree angle, then you could say the sun was 45 degrees in the sky.
And that would mean what? Why would the sun be 45 degrees in the sky? I mean, what would that? How would you work that out?
Well, if it was on the equinox, for example, and you were at 45 degrees latitude at your local solar noon, that is how high the sun should be.
Oh, that was what we were trying to work out, our latitude then. So because the shadow, like, could you not just wait until the shadow was the same length as the thing, and then say, oh, well, now we're at 45-degree latitude?
So depending on where the subsolar point is on the day, like today it's about 8 degrees north. So wait
a minute. What do you mean by that, subsolar?
That's the point that the sun is directly above.
Right, so where are you measuring this 8 degrees north from?
If you were at 8 degrees north, the sun would be 90 degrees in the sky.
If you were at 8 degrees north, how do you know if you are or when you are at 8 degrees north?
If the sun were directly 90 degrees above your head, then you would know that that's where you are.
What, if the sun's above your head, then you're at 8 degrees north?
On today's date, yes. And it's also noon at that exact point in time. But regardless, knowing that the subsolar point is above 8 degrees latitude today, you would then subtract that from your latitude. So let's say you're at 58 degrees. You would subtract that from your latitude, and you would expect the sun to be at the what do you call that? The complement angle. So it's 50 degrees. The complement from 50 is 40, so 90 minus 50. And so you would expect the sun to be at an elevation of 40 degrees in the sky on today's date.
See, like this test that I think you're trying to pair somebody up with somebody else to do this, are you?
Oh, pairing several people up with several other people.
Okay, right. Well, that was what I was asking. It's like, what would we have to do in order to do this thing?
Well, it's written simply in the thing that I linked, but
you can't explain it.
It's just, yeah, it's like I said, it's written simply, but it's also as simple as just confirming that at your local solar noon, the shadow that's produced is directly pointed north, if you're north of the equator. That's it.
So, sorry. The shadow is pointing directly north.
Yep, that will confirm your local solar noon.
It will. Right. So how do we know north?
Well, you can use a compass.
Right. So what you're saying is then that whenever the sun goes from it goes from the east to the west over the year, and that changes. But at whatever time the sun is pointing north, the shadow, sorry, is pointing north, then are we saying that is when it's perpendicular to the east-west? Is that the north you're saying, or are you saying magnetic north is different to the solar north?
Yeah, if you point a compass at north, you're going to find that it points north, so it's not going to matter if it's the geographic or the...
Yeah, but that's a different north than the east-west sun.
Sure, but the compass will point there, especially from as far south as we are.
So you're saying that the solar noon relates to the magnetic north, not the solar north.
Yeah. What I'm saying is, from our position, a compass is going to point directly north, which is going to mean the same thing. It's not going to be able to tell the difference between magnetic north and geographic north from the positions that we are.
Yeah, but the
south,
solar north is different, right?
Yeah, they're different positions, but a compass is not going to be able to discern that. Like, if you were to look at a compass north...
Yeah, a compass doesn't do anything to do with the sun. It's got anything to do with the sun.
What I'm saying is, if you had a compass that was pointed to magnetic north, and you used the sun at your local solar noon, and you look at the shadow, they'd be pointing in the same direction, because it's such a close distance from how far south we are.
It moves massively, the sun. It sets in a way different position.
Yeah, but we're talking about the North Pole, like the solar, or the geographic north.
Yeah, we're talking about
north.
The difference between a perpendicular. It is. It's different.
Yeah, right.
You've never checked.
For some reason.
Well, is east-west perpendicular to north-south?
Yeah.
Right, okay.
Yeah.
Now, so if the magnetic north, does that alter as much as the east-west maneuver of the sun takes?
Say that once more.
On the equinox, when the sun sets, have you ever checked what the difference is of where the sun sets?
It sets for everybody directly west.
Right, so are you going to say that whenever the sun sets, it always sets in the west?
No, you just said on the equinox. On the equinox, for everybody, it sets directly west.
Yeah, but there's two equinoxes, and the sun sets in a different place on each, doesn't it?
No. No, it doesn't.
Yeah, it does.
For each person in the world, on both equinoxes, it sets in the west.
Have you ever checked that?
Yes, I have. Twice a year. I do tests on the equinox.
Do you do a
every
sunset
year.
test from the same place?
Well, we do
see the sun
local,
set in a different position.
several tests on the equinox. This one, what I'm describing or that I posted about now is one we're doing regarding a few things, but yeah, the last few times we've done it regarding a few things as well. But that is one of the peculiar. It's one of the strange things about the Earth, depending on what model you observe, is that it sets directly in the west and rises directly in the east on those days from every position on Earth.
Okay. So, okay, so the sun does change positions, right, in the sky. It does set in different positions, doesn't it?
Sure, throughout the year.
It's not always in the west, is it?
Only on that date. But yeah, every other day.
So is that when we're doing this test then?
No.
No, we can do this test at any time.
Indeed.
Right, so how do you know where north is?
You can use a compass.
Right, so we're using magnetic north when we're dealing with the solar.
That would suffice, yes.
You not see a problem there?
Well, I've just told you why there wasn't one, but I think that you ignored it purposely. But from our position south, those two locations aren't far enough different from us that we're gonna have two different directions to point at if we were pointing at the magnetic north or the geographic north.
Okay. Well, you've not sold me on this because I don't know what we're meant to be doing. So count me out until it becomes a bit more understandable as to what you're doing. But I mean, I've got compasses, I've got sticks. Sure, I can make a shadow. Well, we're in the UK. We usually struggle for that. But is that all we've got to do then? Is just measure a shadow?
Yeah, just confirm the direction that it's pointing at that time. You can capable of doing that.
Kosho, you ought to go on ranting 'cause he's live now.
Yeah, put it out. Big test. You get some people helping you.
The very first time I went onto Nathan Oakley's show, it was to promote the very first time I was doing this test, or a test like this one.
Oh, that's where you went wrong. You went to Nathan. Ranty's quite fair if you jump on and say you want to present something.
Yeah. Maybe I'll have to put it together more, because I've only just written this up because I was inviting people to do it, but it's easier when you have something.
Yeah, it might be good if you can get like a flat earther and a glober together. I mean, that'd be brilliant, wouldn't it?
Yeah, but I've learned from experience that doesn't make a difference. The very first test I did, I was trying to include both flat earthers and globers, and the person who gave me the most data was actually a flat earther. And even that flat earther himself, regardless of the fact that the data confirmed the globe, he just argued that it confirmed the flat earth for some reason.
Oh, right, you've already confirmed the globe then?
Sure. I wrote a 10-page paper about that test. Put all the data out there.
The sun is the key factor here in terms of reflectivity. Let me just say, at the start of your video yesterday, Ranty, you showed the lighthouse, right? And there's a gap in between.
That was the goal now. I'm not worried about if flat earthers and globers are doing it, but that was my goal before, was to put tests together that flat earthers and globers could do so that they could agree on the results.
Is this sort of like an Aristophanes type thing?
Well, that test was the one that I did 2 years ago, I guess now.
Yeah, the
that
one
was similar to his test.
Fight the Flat Earth was going for the world record, wasn't he, with George Musa?
Sure, maybe.
I don't think it worked though, did it? I mean, it must still be up for grabs.
I don't keep up with him.
How many did you get in your when you did your 10-page paper then?
I did 23, and I had heard later that Sly Sparkane also did the same thing on the solstice, though, and also used 23 people.
Wow. And what did you have? Two different models to map it on?
I did, yeah.
Under ideal conditions.
That was the purpose of mine, was to make predictions on what we would find on a globe, and make predictions what we would find on a flat plane with a sun, local sun, and to see what the results they matched which predictions.
Okay. Did you you were measuring angles and stuff?
Yeah, very similar to what I described earlier with you.
So you would have been using Euclidean geometry?
Yes, indeed.
Okay. And straight light rays?
Yes.
Right, so you use straight lines and angles that straight lines to prove a globe.
That's right, yeah.
It's pretty impressive, that.
I thought it would be sufficient, especially because the predictions are based off of, you know, which model was correct. So you wouldn't be able to just guess the predictions. You'd have to infer the predictions based on whichever model you were using. And the predictions matched perfectly, all 23 of them, to the globe predictions.
So you predicted that the light would be in a certain direction.
That the angles, the shadow, the angles of the elevation angle of the sun from those different positions on the subsolar, I mean at this local solar noon on the equinox, from those locations.
Yeah. That the sun was in a certain position. See, no, it's not like you being able to predict where the sun is, because I think I could do that as well. So, you know, the sun's going to be in a certain part of the sky at some point during the day. I mean, it's always there, right? It's not brilliant prediction capabilities, is it, really? What is fantastic is the way that you use in angles, which is straight lines. And the light from the sun, which is also a straight line in a ray, to cause a straight line on an angle. And then you're measuring that angle from a straight base underneath, which I presume is a horizontal. Right? When you're using that elevation angle, you would be using a horizontal. Like a straight line horizontal, right?
Wait, where's the horizontal?
Well, what are you measuring your angle from then?
Like the ground being horizontal?
I'm just asking you, where are you measuring your angle from?
Right, so you would make a tangent line below your feet, which would be, I guess, the horizontal you're referring to.
Right, so that's a straight line. That's what I'm saying, yeah.
Right.
Yeah.
And then the angle to the sun would be the other line, and then you would just see the angle between the two.
Yeah, so that would be two straight lines.
Yeah.
Yeah. How does that straight line angle turn into a globe?
Well, because they're not really straight lines, you're just using it to make your triangle. But a tangent line on the surface, like a tangent line specifically, just means that it meets the Earth only at the position that you're at. So it makes a straight line. It goes off into infinity, but those points don't ever touch the Earth again. So.
Okay, so you're presupposing a tangent. Well, by the fact that you say tangent rather than just horizontal, you're already presupposing a ball, right?
Indeed. In order to make the predictions for the globe, I had to presuppose a globe to make those predictions. The same way I had to presuppose a flat plane with the sun being local to make predictions for that.
Sorry, the sun being local?
Mm-hmm.
Is that it? Is that what you've got?
That's what I had to make predictions for, yeah. If the sun were far away and the Earth were flat, but were sufficiently far away, it would be the same distance in the sky, or the same elevation in the sky for everybody everywhere.
Okay,
so it would have to be local if the Earth is flat.
On both of the predictions then, you are predicting that you know a position for the sun?
No, on both of those predictions, I'm making predictions based off of which model it might be.
Yeah, and in
And if
both
I-
of those
the-
models, you have a position for the sun, because one of them
No.
you call local.
No.
What does
neither of them-
local mean then?
Yeah, neither of them started out with a position for the sun, but for the one predictions for the globe, I had to confirm that they came in parallel, and so you have to infer that they're far away enough
wait,
to be
whoa.
parallel.
What do you mean parallel? What came in parallel?
Came to my mind when the sun is the great
You just popped
Do I have
that
to
in
explain
then.
every word that I use?
Yeah,
to
yeah,
you?
because you just popped in
I'd
parallel.
rather
They
not.
came in parallel. What are you talking about?
What do you think I'm talking about?
I don't know. Like what you just said, it popped in from somewhere. Something came in parallel.
And what was I referring to when I said that?
Don't know.
Alright. So you don't remember that I
The-
said that the sun was close and local for the flat plane?
Well, yeah, you said the suns came in parallel then. Is that what you had? You had parallel suns in the local model, or parallel? They were both parallel. The sun from the faraway model and the local model. So it's just a speed of movement difference from the one that's close.
I think it might be easier if I just post the paper for you, because I can't explain these very minute details, because there's so many of them. Hold on.
Did you not sort this, or have you picked this up from somewhere else?
There's a paper there, and it's got the measurements and the everything you'll need.
Shrunk.
Oh, don't worry about the title. This was a working this was a working form. I sent in
millennia ago. Do you reckon Aristophanes was a real person?
most likely.
Most likely. Do you know the problem I have? You guys really don't like geometry, do you? And like you like to keep swapping and swapping between different types of geometry. And I think that's because there's a certain geometry that doesn't work. You can't get the globe to work with that geometry, and that one's called Euclidean geometry. You guys really don't like it, do you? But Aristophanes, that's the geometry that Aristophanes must have used, right?
Hey, hang on.
And you're trying to do the same thing,
That article, Jim, that article
aren't you?
only cites the video.
Also trying to use the Euclidean geometry to prove this thing of yours. But can you not see the problems?
With your ways of thinking?
No,
Yeah,
with the problems within Euclidean geometry.
It's almost like that try thinking is like on your to-do list or something. But I've never said I had a problem with Euclidean geometry. It's just fine. It's fine geometry. I don't have some kind of prejudice against it. So because of that, everything else that you said is kind of irrelevant. And I don't find it odd that Aristophanes used Euclidean geometry because it's a fine geometry.
Yeah, it is. It's the finest. Flawless, I'd say. Wouldn't you?
No, I would not say it's flawless because the
got-
biggest flaw in
it's
it
got-
is the
okay.
reason why they had to make non-Euclidean geometry. It had a flaw
what
for 2,000 years almost.
What flaw's that?
That fifth postulate couldn't be proven.
What do you mean it couldn't be proven?
Yeah, it couldn't be proven.
How
like
could-
on a sphere, for example.
How could it not be proven?
Well, it was proven to be incorrect on certain surfaces, so they had to make new geometries because of that reason.
What? Because it couldn't prove a globe. That's why they
No.
had to make a new geometry.
No, it didn't have to do with the surface of the Earth per se. It just had to do with the actual postulate itself.
And what was wrong with it? You have read it, haven't you?
Sure. Euclid's, I've read all his, what do you call it, the elements, all that kind of stuff.
Well, it just states that if two lines bisecting another line, intersecting another line, that if the lines are produced to an infinite length, they will meet on the side that is less than 180 degrees. I mean, do you have a problem with that?
Well, in non-Euclidean geometry, like I said,
No,
they
that's
meet.
no,
In
that's
Euclidean
not.
geometry,
No.
they don't meet.
Yeah, but the Euclidean geometry is the one that you said they had a problem with.
Yeah, they had a problem proving that.
Proving what? That the two lines would meet on the side that is less than 180 degrees.
No, about the parallel lines.
No, that's
Don't
a
meet in
no, the
Euclidean
parallel
geometry.
lines is a definition, not a postulate.
I mean, they're all postulates.
What do you mean they're all postulates? No, the
Yeah, it's
definitions
called
are
the fifth
definitions.
postulate.
Yeah, the definitions are the definitions. The postulates aren't postulates. Right? They're not the same thing. Do you want me to read you the definition 35? Have you got Euclid or ever looked at it or anything?
Yeah, that's what we're talking about. Euclid's fifth postulate, the one about parallel lines.
Well,
right?
okay, well, I'll give you the last definition 35, that
Well,
states...
we're not talking about that. We're talking about the fifth
that
postulate.
states parallel straight lines are such as are in the same plane and which being produced ever so far both ways do not meet. That's a definition.
Okay. And do you have the fifth postulate in front of you?
I have the 12th axiom in my book, yeah. Want me to read it for you? If a straight line meet two straight lines so as to make the two interior angles on the same side of it taken together less than two right angles, these straight lines being continually produced shall at length meet on that side which are the angles which are less than two right angles.
And the problem was that they hadn't had a proof for it.
Which
The other postulates had proofs for
it's
them,
an
but they didn't have proof
axiomatic.
for them.
It's an axiomatic system. Euclid's Elements, the whole book, Euclidean geometry, is an axiomatic system.
Proofs for the other ones.
You get proof for everything.
Yeah, postulate. That's the whole point. There's proofs for the other ones, but there's not a proof for that
Yeah,
one.
but there is, because a parallel line is defined as not touching, not meeting. The fifth postulate, as you call it, the 12th axiom I'll call it, it doesn't state anything about parallel lines. It just says where the lines will meet.
Also called the parallel postulate.
No, you might call it the parallel postulate, right? But there
Mathematics
was
says
already a
that.
definition of parallel straight lines.
Yeah, in mathematics, that postulate is referred to as the parallel postulate.
Mm-hmm. Well, as you can see, I've just read. It doesn't say anything about parallel lines, does it? It just says where the lines will meet on the side that has less than 180 degrees.
Well, if you look at parallel
Or
postulate,
less,
you'll see
sorry,
it's
less
referring
than
to the
two
same
right angles.
postulate.
But can you explain why it's a problem?
Because there wasn't a proof for it.
It's not a proof for what? That the line's not touching?
For that axiom being true. So just consider true until they discover
Because-
non-Euclidean geometry, which refers to curved surfaces.
Well, this refers to curved surfaces as well, doesn't it? Because it's a sphere. That's within
Well,
Euclidean geometry.
Yeah, curved surfaces are not within Euclidean geometry.
A sphere is in Euclidean
A
geometry.
sphere, but not the surface of a sphere.
Not the surface of a sphere.
Right. There's nowhere in Euclidean geometry where they talk about the surface of a sphere.
why would they talk about the surface of a sphere?
Sorry, say again?
Why would they want to talk about the surface of a sphere? What would you want?
Well, let's say you want to talk about the Earth or a ball.
No, it's like this is
like
geometry. Like, why would they want to talk about the surface of a sphere? You think that for some reason they would want to conflate the surface of a sphere with the Earth and put that into the geometry? Do you think?
If need be, which seems to be the case. The Earth is a sphere, and geometry is measuring the Earth. You would think that measuring the surface of the Earth would be included in geometry, which now it is.
Okay, but why would parallel lines not meeting be a problem then?
Well, because it doesn't work on curved surfaces.
So you want parallel lines to touch them, right? Intersect.
No, that's actually how they behave. When they start out parallel, they don't end up staying parallel, and actually aren't considered parallel. But they do start off that way. We went over this the other day.
What, that you say that parallel lines don't stay parallel? Do they intersect at any point? Parallel
Well, yeah, they're not
lines.
even considered parallel lines because the fact that they don't stay parallel. They do intersect. But you can start them off parallel, head them both in the same path. Their paths are both parallel, but they will end up intersecting.
Okay, so is that what's wrong then with the Euclidean geometry?
That's why they couldn't prove it. You know? But
They did
eventually.
eventually find out that parallel lines aren't parallel, and they do, in fact, at some point come together or intersect.
No.
Which
What they did was they just described a whole new geometry that applies to curved surfaces. So in Euclidean geometry, you can have parallel lines, and they will infinitely go off and not meet. But then you also have curved surfaces, which do not behave that way.
okay, so the latitude lines, like we did this before, you were trying to use them before within your maths. Are they parallel?
Latitude lines, no, they're not straight lines. They are
They
parallel
are.
planes.
They
in
are
three-dimensional
known
space,
as
but
parallels, aren't they?
they're parallel planes in three-dimensional space, but they're not straight lines.
Why did you say straight lines? Like, what's...
Because you're not going to call them parallel if they're not straight lines. You can call the planes parallel because the planes, they do run parallel to each other.
So there is a plane in spherical geometry then, is there?
No, what you could do is you could create a plane that would intersect the Earth at those latitude lines. That would like cut the Earth right there. Those planes would then be parallel.
But them planes wouldn't be spherical geometry, would they? They would be Euclidean geometry, right?
Sure. They're not just in
Okay,
planes,
so
but
we
yeah.
can use Euclidean geometry to intersect planes within spherical geometry that would be parallel if they are in the Euclidean space. But since we're dealing with spherical geometry that is a two-dimensional representation of a sphere, that we can have planes intersecting that two-dimensional surface. Yeah?
And you understand, in reality, there only exists one Earth. And when we talk about geometries, we're talking about different ways of describing it. And so what you're doing when you say you can do this in non-Euclidean and this in Euclidean, you're just talking about it in two different ways. And so that's what's making it confusing. But
so it's the
always gonna
same
exist
thing
one
then?
Earth. Yeah, I've told you this about the GPS coordinates.
So you think you can describe something as being both parallel and parallel but not parallel intersecting lines at the same time, and just choose which geometry you want to explain it in?
No, not at all. What I said was let's say you have a three-dimensional basketball or globe toy or something, and you have all the latitude lines. They would make lines that went around the Earth, And if you had a flat plane, you could intersect the Earth at all those lines, and those intersections, those planes would all be parallel.
Yeah, but
But
that's
if you were to take those lines
mixing
off
up
of,
two
if you were to take those
different
lines off the ball,
geometries.
they would not make straight lines.
If you were to take the lines off the ball, really?
Right. If you were to take the lines off the ball and look at them separately, they would not make straight lines. They would make circles.
They're on around the ball, aren't they?
And the thing I'm describing, yes.
You got your mic open there, Kosho. Or is you listening? Everybody else listening?
I mean, did you understand what I said?
Hi guys, who's listening? Who's the team? Who's the team, Kosho?
Posted a video for you a couple of minutes ago that might.
Yeah, I've already seen that. That's old school. Saw that about a year ago. It probably.
I'm surprised at all the questions you have, man.
I'm just trying to work out you with your geometry and your mixing. Who's advising you? Because they're not doing so well. You can't just flip and flop between different geometries, and you can't use one geometry to describe another geometry. It's a bit ridiculous, because you don't seem to understand what a geometry is. It's funny though. Who is it you've got helping you? Is it one of the trolls? There's a few trolls that like to pretend that they know what they're talking about. They sound like they've been talking to you as well. Sounds like this sort of a thing. You can have a Euclidean plane that is parallel, that cuts through the latitude lines, but the latitude lines aren't actually parallel because, as you say, they're not straight lines. Well, on your model they're obviously on a circle or on a ball, so they're obviously curved lines. There's no straight lines on a sphere, is there, Kosho? Or do you think there are some? Are there any straight lines on a sphere?
Well, they're not described as straight lines, so
they're not described as straight lines.
Yeah, geodesics would be what you're probably referring to, but they're not.
No.
We're just straight lines.
Is that what they call all lines on a sphere? A geodesic. Is that what you call it?
Line. That's what you call a line that's created, the shortest line between 2 points.
On spherical geometry.
On a curved surface.
Yeah, in spherical geometry. Because that's what you're talking about, right? Or have you just done a little mental flip over to do some other different geometry now? Or is somebody advising you to do a bait and switch into some sort of other geometry? Or are you talking about spherical geometry? Or are you now talking about Euclidean geometry? Or are you throwing in a wild card, other geometry? I mean, you could always go with Fight the Flat Earth as well. We'll add the fourth one in, right? The Fight the Flat Earth geometry, where you just redefine straight lines as being curved and parallel lines as intersecting.
So I'll explain why I think the question you're asking is ridiculously retarded. Is because I've just corrected what you said about spherical geometry and said yes on curved surfaces. Curved surfaces refers to all of non-Euclidean geometry, including hyperbolic surfaces and spherical surfaces. Yeah. So those are subsets of curved surfaces.
And
so if I say
that's
curved
all
surfaces,
geodesics. Every
so when
curved
you have
line.
Spherical surfaces, then that's not a different geometry. That's just the geometry that encompasses all of the curved surfaces, including spherical geometry.
Well, why were you telling me that a latitude line wasn't a straight line? Do you think, I mean, like, it's obviously not. There are no, like, I'll say it again, there are no straight lines on the surface of a sphere.
Well, it's not even a geodesic. It's not anything. It would make a flat plane in reference, parallel planes in reference to one another, but it's not a geodesic, except for the equator. The equator is the only latitude line that is a geodesic.
A parallel line, did you just say?
Parallel planes.
Parallel plane, right? So there are parallel planes within spherical geometry, are there?
Well, we're not talking. When I say parallel planes, we're obviously not talking about spherical geometry at that point.
Oh, right. So why are you just flipping and flopping between different geometries? We're talking about spherical geometry and the fact that there are no straight lines on it.
Well, yeah, and then you asked me about the parallel planes of the.
No, I asked you why you kept putting in parallel planes. I asked you why are you doing that.
I mean, it's just the truth. It was probably contextual.
It's a different geometry.
Yeah, most people don't have a problem with that. Most people aren't that confused whenever you refer to something in either case, as long as you're making it clear which case you're referring to.
Most people let you get away with it, you mean?
No, it's not about getting away with it. It's just how it's described. Like with GPS locations, I've told you this, that they come in three-dimensional Euclidean Cartesian space.
Yeah, X, Y, Z coordinates.
And you have to translate them into spherical geometry. But in either case you're speaking about them,
you have to translate Cartesian coordinate system.
Yes.
Into why are you doing that?
So that it's readable to people like me and you.
So what? An X, Y, Z coordinate system.
Right.
Is that not readable?
Well, it's not going to tell you anything useful. If somebody gave you your XYZ coordinate on Earth, you're going to be like, wait, what is that? But if they told you your longitude and latitude, you got a pretty intuitive idea.
I'm not too sure anybody would understand what you're talking about with the longitude and latitude.
Most people who are involved in this would.
Involved in
this conversation about the Earth.
I would beg to differ. I
had a conversation with several people about it earlier today.
Don't understand what longitude and latitude are.
Yeah, well, that's exactly what it is.
But I bet if you said go forwards 200 feet and then turn right and go 200 feet and then climb up a ladder and go 10 foot up, they would know which one of them was X, Y, and Z coordinates, wouldn't they?
Well, people who deal with this, like Soundly, who helped. You told me this originally.
Soundly. Yeah, shout out Soundly. Is he in the background there? Is he listening in?
No. The more you say that, the more you
is he not scared? Is he too scared to come in? Tell him he can bring Wardy if he wants, and Wardy can have a talk for him.
Again. You seem kind of mad, man. Like I don't know why you keep referring, like there's other people around or something like that. There's nobody here but you and the people in the room.
You've got an open mic, haven't you?
But,
I can hear it feeding back.
Hear what feeding back?
Your mic, or me-self through your mic.
Yeah.
Yeah.
So what does that mean?
It means you've got a speaker open at your end, so everybody else can hear what's going on.
That's how I hear you.
Okay.
Anyway, about the coordinates, yeah, you have to read them in 3D Cartesian space, which is the way it comes, because it makes sense. X, Y, Z, it's going to be a dot. Those dots wouldn't make sense to us.
Yeah, but like within these coordinates, what you're talking about? Who's getting these coordinates, and what are you talking about?
Whatever GPS system you use, like if you use.
The GPS brings it X, Y, Z coordinates.
That's the way that they're read. But yeah, that's the way they're read. And
okay, it just plots you on a grid, though, doesn't it? It doesn't, like, you don't have to do anything. It tells you with a little dot where you are on a map.
Right, but that's what I'm saying. The data that comes in from those satellites comes in as an XYZ coordinate, with the center of the Earth as an origin.
Oh, it comes in from satellites, did you say?
It does, yes.
Okay. So the GPS works with satellites, does it? on my phone.
Absolutely, yeah.
Jolly good.
Put your phone on airplane mode and you'll see that your GPS still works.
Right, and that's because airplanes can still get satellite signals, is it?
As airplane mode will turn off the mobile service on your phone, but it won't turn off the signal you're getting from the GPS.
Really? Do you reckon it not just... Does that not just mean that they're still tracking you and they still can track you, even though you turned your Wi-Fi off? That, well, you know, the phone has still got some sort of a tracker in it.
Well, airplane mode is going to disconnect the receiver and transmitter.
Okay, and they can still tell where you are?
Well, you can tell where you are.
And you think nobody else can tell where you are?
Well, I'm sure if somebody is tracking you, if they'd like to track you for some reason, they could also tell where you are. Yeah.
Okay, and that's the satellites, right? Well,
they use the satellites to position you.
Right. Can you just work us through that, how that works?
Briefly.
Go on.
It's got to make 4 circles, or 4 spheres. It takes each, whatever 3 satellites that are close, that are able to communicate with you. It'll take the time it takes, I think, for each of them to... It'll ping a signal from your phone to each one of them, which will give them all unique ranges that they could possibly be in. So they could possibly be in some unique range, and then once those 4 are combined together, when they intersect, when those spheres intersect, will be the position that you have to be in. It works the same way with 3 circles on the Earth. Like if you have cell towers, you can ping a signal off 3 different towers, and wherever those 3 towers intersect is going to be the position you're in.
Yeah, so the satellites, they're pinging my phone, or is my phone pinging the satellites?
I think your phone acts as the receiver, so...
Okay, so how does it know... how does it know where the satellites are?
To be honest, I'm not a complete expert, so I gotta think for a second. I forget which one, where the signal comes from and goes first. I know that your phone is the receiver.
Yeah. Well, then it makes sense that it comes from the satellite, the signal. But you'd only know when the phone received the signal, right? Like, that'd be the only information the phone would get would be,
right,
I'm a satellite. I'm satellite number 1. And I'm sending out a signal to every phone, everywhere. And you've just received it.
Well, yeah, like they said, the time it takes for the ping to occur.
How does it know how long it takes? Because your phone just gets the signal.
Like I said, I'm not an expert.
No,
that would just be bastardizing the whole...
It is a bit tricky, isn't it?
If I told you.
Because, like, your phone would just get, like, I don't know, I presume, how many satellites do you think are up there?
Sometimes 40. I mean, from America, we have, like, 4, but there's Russian ones, there's other systems.
So all of those satellites are just sending out signals, right? Going, I'm here. And then
like I said,
everybody's phone just receives that signal that says, hi, my name's Dave, I'm Satellite Dave, and I'm communicating with you. And then your phone goes, oh, hey, Dave's just sent us a signal. And then, whoa, hey, wait a minute, there's Shirley. Shirley's just sent us a signal. Oh, wait a minute. Dave's mate, John, Dave, and Shirley have all... Oh, wait a minute, there's another one. Ezekiel just sent us a... And, like, you know, like, there's just loads of bombarded to your phone. But how does your phone know? how does it time it or whatever? You know, how does it know how far away the satellite is and how to triangulate the position? How does that work?
Okay, it says here, to accomplish this, each of the 31 satellites emits a signal to receivers that determine their location by computing the difference between the time it was sent and the time it was received.
Okay, well, how does it know when it got sent?
Well, I suppose that's in the signal. That's probably the signal that's transferring, is a time signature. And then you receive it at a different time signature. Oh,
man, that sounds brilliant. So how often are these time signals going out?
All the time.
Oh, like every second or so. So every second a satellite says, here's the time I'm sending this signal. It's dinner time. And your phone gets the signal and says, it was dinner time when Dave sent this signal. And how long do you reckon that distance would take? You know, like how fast?
So it says your GPS satellites carry atomic clocks that provide extremely accurate time, and the time information is placed in the codes broadcast by the satellite, so the receiver can continuously determine the time the signal was broadcast. Brilliant. So I guess our assumption was correct.
So they have to have atomic clocks up there, and your phone, I mean, how long does it take? I mean, how far away are they?
I'm pretty sure about 20,000 miles.
They're 20,000 miles, and how long is it? How fast does these signals go?
Close to the speed of light.
Speed of light. So how long would you calculate that?
Less than half a second, like maybe a fifth of a second, less than that.
Okay. So your phone would have to be really, really accurate, right? I mean, can you imagine the computing power of all of those signals coming in from 31 satellites continuously? And then you can turn your phone off and it's still receiving all of those signals from the satellite saying, hey, my name's Dave, I'm here, it's 12:01 now. And all of them going into your phone, and your phone's going, oh, well, I'll have to work out, well, that took, well, what time is it now? It's like 0.05 of a second difference between that and that where Dave, would it also it would have to send where Dave was, right? Because just knowing a time that Dave sent the signal would be no good for your phone, because your phone would just get a time. Hey, I'm Dave. It's 1 o'clock. And your phone would go, well, who's Dave? Wait, where's Dave? It's 1 o'clock. I know he sent it at 1, and it's reached my phone here. Is that what your phone does then? Does your phone work out where the satellite must have been at the time? But then your phone would just work out where satellites was. I mean, that wouldn't help you know where you were.
So the 4 spheres come in. So let's say you've only signaled 1 satellite, and you've got a distance now.
No, you've got 31 satellites constantly bombarding you with what time it is.
Someone's explaining something to you, and you're not going to get it if you're asking questions because they haven't finished what they've said yet.
I'm not asking questions. So of course you're going to have questions.
And of course you're going to have questions because I haven't finished what I said yet.
It's not a question. I'm just telling you the satellites are just sending the time.
Your question would sound ridiculous. I'm talking about when you get one signal from one satellite, a sphere is created around that satellite from whatever distance that it just calculated. And that's why you need 4, is because only once you have 4
satellite distance spheres calculated.
Once those 4 spheres are known, then they see which point they intersect at.
What spheres are known?
The one I just explained to you.
The one around the satellite, because the satellite sends a signal constantly, you said, to everyone's phones. So is it constantly making spheres every time it drops a thing? And again, how does it know? How does your phone know where the satellite was?
Just explained it to you, but I'll do it again. but you probably have to not talk this time. When the satellite sends a signal, one of them, let's say that you see 20 of them in the sky, but one of them sends it at a time, so that it can, so you can understand this. They're all being sent to you, so don't get confused by that. I'm just describing one for now. One gets sent to you, and you now have a sphere that's created around that satellite. So you don't know where you are yet because you've only have information from one satellite. You could be anywhere in that sphere around that satellite, but then another satellite is you get information from that one and the other one and another one. And once you have those 4 spheres, you see where they intersect, and the position that they intersect is your location. The position of those satellites are also known by the satellites. The system itself is what computes it for you.
The satellites know where the other satellites are.
Say again?
The satellites know where the other satellites are.
They all know. They all have a specific location of where they are, and they can communicate with each other. So.
Okay, but they're just sending out a signal of what time it is.
That's the continuous signal they send out. Yeah.
Of just
Probably
of the time.
That's the one that you receive.
Yeah. So you just know where satellites at what time satellites are checking.
Well, they know. I mean, the satellites know what time, and they send you the time.
Okay. And
that's the signal that they're sending. It says.
And your phone measures what, the difference in time?
I don't think that it's in your phone that makes the computation. I think one of the satellites does. But let me see.
Sorry, the satellite makes the No, the satellite. You said the satellite just sends a time.
Yeah, no, but I think one of them acts as a
All right,
receiver.
I'm Dave. Satellite.
Let's find out
Dave,
now.
and it's dinner time.
Yeah, it says the receiver uses the difference to compute the distance. Hold on. From the receiver. Okay, so it either needs 3 signals, and the receiver has to have an atomic clock, or 4 signals and you don't need an atomic clock. It says. Let me see where it says. The receiver uses the 4 satellites to compute the latitude, longitude. I'm trying to see where the computation actually takes place.
Yeah, I'm trying to work out.
It has to be in your phone.
Yeah, find us out how it knows where you are, because it's just sending. These satellites that you're talking about are just sending a time.
Oh yeah, time for each of those. So if you have all 4 of those information, if you have all 4 of those positions and their times that it took you, so we have a sphere around them and their position. If you had a system in your phone or in your Garmin or whatever it is that you're using. To compute that, you could easily compute that. So they have to use 3-dimensional space and Cartesian grids, because those satellites' positions are going to be translated in 3-dimensional grids, and then it's going to create spheres in 3-dimensional space, Euclidean geometry, and where those 3 or 4 spheres intersect, is going to give you an XYZ coordinate, and then you have to translate that to the non-Euclidean surface of the Earth.
Right, does it?
Latitude and longitude.
I think you're missing. It sounds like it needs to go back, the signal. Because just knowing the time, surely you can't. Can you work out a way that a satellite could just send a time?
Well, it must also send its position as well.
Yeah.
See.
I think I heard somewhere that your phone is meant to know the position of all of the satellites. Sounds a bit fantastic, but I mean, I think that's what I've heard. You might want to check that though, just to make sure.
It can read this. That's why I said if you put your I have a app called Physics Toolbox Suite, and it's got the raw GPS, or it has the GPS data from the different satellites. It tells you which satellite's coming from, and you can you can see which satellites you can see and where they're at and all that kind of stuff.
So you like for the satellite to send that as well as the time. You would imagine that it has to. It would have to be pretty exact at where it is.
Yeah.
Right now, how would you reference the position of a satellite and
I'm saying
the speed?
yeah.
How would you know?
Well, it's referencing XYZ coordinates.
Really? And what
Yes.
do you reckon that would be travelling at? You know, what sort of speed? Did you say 20,000 miles?
If I remember correctly, it's somewhere 14 or 15,000 miles per hour.
Okay. And a distance of like 20,000 miles ish. I mean, like you'd hope it was to be accurate, right? Because you're dealing at it's sending a signal at the speed of light.
Mm-hmm.
Right, spinning at 14,000 miles an hour. Right, and it has to send I'm here. Hey, I'm Dave. It's dinner time. I'm here. And then by the time the signal actually gets to the phone, right, and your phone's got to then get all of that information, hey, I'm Dave, I'm here, and compute it into a distance
Location, yeah.
Distance location of what, where this satellite was.
Mm-hmm. Yeah, computers are fairly fast. It
Your
says I can see
phone, I mean, like your phone's doing this with every satellite that's up there all the time.
It says I can see 18.
Yeah,
I
you
can
can
see
see
18
18
satellites right now.
And so how often is it sending this signal, and how often is it making this computation?
It's sending it constantly, and it says that my accuracy is within 15 meters.
15 meters. Is that like a horizontal distance, or is that a vertical distance?
It's just a accuracy of where it is.
Right. So is
So
that more accurate? Because 15 meters, is that plus or minus 15 meters? So that could be like a 15-meter radius around you. Right.
Exactly.
What about, is that like a spherical radius though? So could that be 15 meters up and 15 meters down?
So the location it's saying to me could actually be 50. It says 10 meters now. It could actually be 10 meters in any direction, any three-dimensional spherical direction. From
so that would be absolutely useless for measuring the water level over a mile. Right,
really
because we're talking about 8 inches, then if you only got an accuracy of 10 meters, then that's out, right? We can count that out as a means for accurate measurement, right?
Yeah, I don't know why you would.
I'm so glad you've come round here tonight. We've just dismissed GPS as a rubbish accurate measurement thing.
I mean, it might come in handy in some regards. I know George used it when he did his lake experiment.
Experiment? I don't want to get off track. I won't want to get off track. So, 15 meters. Oh, so George used it, but he was like within an accuracy range of 10 meters.
No, I mean he used it for some reason. I don't think he used it to get. I'm not sure in what regard he used it. I just know it was included in what he was doing. I'm not sure when, what context.
Okay.
But he also used a much more accurate than my phone. Actually, I think he even said the accuracy of the GPS he used.
Right. So are there surveyors that only use GPS surveying techniques?
I have no idea.
No. Okay.
I don't see why there would be for somebody who only uses GPS, but I know that they use it for certain things because they have they use like a station, and that'll help them determine different heights and stuff. But I'm not sure how accurate that is.
Yeah, well, I mean, like, it wouldn't be, because, I mean, when I went to go and get my auto level, I asked them for which would be the most accurate. And they said the auto level is the most accurate, because that's within the millimetre. I mean, you're saying 10 metres-ish. I mean, that's pretty bad accuracy, right?
Yeah, sure.
I mean, I mean, nobody would survey with the phone like you.
Yeah, nobody would find their location with an auto level. They're two different tools for two different purposes, so I don't know why you're bringing them up.
Yeah, it's okay. But, I mean, yeah. Good. I'm glad we got the GPS for surveying methods out of the way if we want to sort accuracy.
It says the positions of the targets, this is for George's test, were measured by Jesse Kozlowski to centimeter accuracy using his differential GPS equipment and post-processing the collected data. I'd have to look and see what that entails, but it's obviously not just using like a phone. I think he's got some kind of, like I said, station. And that station helps you give you more accurate information.
But he just measured the positions, and then George did what?
I'm not sure. Like, I could post
see. I think differential leveling. Right. That's not GPS. Did he say he did? Let me have a look at that. Is that the one that you just read that from?
Yeah, about measuring the targets and that kind of stuff. So it's going to all be part of this document. Hold on, here's this. And this talks more about the differential GPS equipment. There's a picture of Jesse using that tool, a Trimble GNSS system.
Oh, right, I see. George planted the targets at planned distance from the observer location. He used his GPS receiver to locate their planned position.
Oh shit, I have to go get lunch, man.
Differential GPS arm. Thanks for sending us this. We'll go over this.
Yeah, this has got a lot of data on it. I'll give you the main page too, but I gotta run.
All right.
Yeah, but nice chat.
Cheers for popping in.